Okay, so good morning, class. Right, so just to check, can you guys hear me now? Okay, thank you. Okay, so before we begin our discussion today, can we do a quick recap of what we have covered last week? Any volunteers from the class? Can anyone share what he or she recalls from last week's discussion? Anyone? Yes, Mr. Gonzalo, please proceed.
Last week po, we talk about some electronic devices po like conductor, semiconductor, and insulators po. Tapos, na-discuss din po natin yung iba't ibang common semiconductors tulad po ng mga silicon, tsaka po yung reason kung bakit po mas ito yung ginagamit kumpara sa carbon. Ito talaga.
All right, thank you. Okay, so previously we have covered the properties or electrical properties of some materials that we use no, for various electronics applications. I think we've also done at least the basic, we've covered the basic explanation on how semiconductor diodes work. No? And okay, so this morning, although our regular session duration is cut into half, no, at least we want to, or we intend to still do some progress this week by covering uh, right, so the principles of operation of semiconductor diodes. So okay, so here are some of the concepts. So, okay, so here are some of the ideas that we've shared last time. And if we are to recall, the semiconductor diode is created by forming or joining an N-type material and a P-type material, both of which are produced out of intrinsic semiconductors. Well, after some chemical process called the doping, we've introduced or altered the electrical characteristics of the semiconductors to become uh, an N-type, which is a majority carrier, and the P-type, which is, or an N-type, which has the electron as the majority carrier, and the P-type, which has the hole as the majority carrier. Taking note that the hole here is what we uh, where we makes use of the designation of the positive. No, albeit we're not designating the positive in the case of, or we're not actually treating proton as the positive, but the vacancy or the absence of electron, which is in this context of semiconductor physics we refer to as the hole. No? And that the in to continue with this discussion, we are have to be aware of the modes of operation, no, of the semiconductor diodes. We have to understand the following modes. Now, the first is the condition where we do not have any sort of a bias. The term bias, I think, is somewhat of a buzzword in the current social media trends. No, all right. So here we will learn in the context of electronics the proper biasing in semiconductor diodes. We have forward bias and the reverse bias regions. No? And later we will see how we can describe the AC DC characteristics, no, of the diodes. Now, if we try to apply AC or DC inputs, and we will be introduced as well with the concepts of practical and ideal semiconductor devices. All right, so for the all right, so for the hold on, let me just try to adjust my volume here. All right, so okay, so a diode is constructed by forming the PN junction. All right, so please just don't mind the background noise here. No? Anyway, we okay. So last time we've learned that the semiconductor diode is formed by uh, joining a P-type material and an N-type material in such a way that a junction is formed in between them, and that the electrical uh, responses of these junction creates the switching action for the semiconductor diode. Then if we stick two pins into the device, one is connected to the P-type material and the other is connected to the N-type material. We refer to the one connected on the P-type material as the anode, and the other one is the cathode. No? And here is the symbol before us and an actual physical device. So it's in terms of the typical model uh, 1N4001 or 4000 series is in millimeters dimension. No? All right, so and that right, so the actual semiconductor material is even smaller than this device right here. No? I think you've seen this before, but much of what you can see in that black uh, thing right there is much of which is the enclosure itself. So it's possibly made of plastic or epoxy, depending on the manufacturer or the construction. But the semiconductor piece, or if you think of the PN junction or the P type and N type material formed or fused together, it will just be a very, even a relatively smaller than what you're actually seeing. So this is just the enclosure, and the actual device is inside of it, which is really a very small, piece of semiconductor materials joined together. All right, so as I mentioned, the P type or the P region is called the anode, then the N region is called the cathode, and we can it can have three operating modes or conditions. The first one is called the no bias condition, where we do not apply any sort of voltage across the pins. And then we have the forward bias, where we apply positive voltage to the p-type material. This is relative to the cathode, or the n-type material is being applied with the negative potential. Also, we can connect the diode the other way around, such that the p-type material is connected to the pas or the n-type material rather is connected to the positive voltage supply, and the p-type material is connected to the ground or the negative part of the supply. And this case is what we refer to as the reverse bias condition. So in a no bias condition, so this is essentially the default setting. Much of the principles here in the formation of the junction and the depletion region have been covered in earlier discussions. And that, well, again, in the default or the no bias condition, the majority or the positive ions, the majority from the p-type is sort of migrated to the other side, and the same thing happens for the majority of the majority carrier of the n-type material, which sort of migrated to the p-type side. Only in the surface, no? Only this happens in the surface, and that the interaction of charges in between them creates some barrier, no? So this barrier sort of prohibits any further migration of ions in between them. You can think of this event as in the case of uh, an overcrowding. There is some sort of overcrowding that this region gets filled up already with the charges, and no further movements can occur uh, after that the formation of such barriers. All right, so okay, here's some sort of explanation to help us further better figure, how these things actually happen in the default condition.
In our previous tutorials, we've discussed the basics of semiconductors, bandgap, current carriers, and their classification. We learned that in order for a semiconductor material to be useful, it needs to be doped with an impurity atom, and it could be a pentavalent atom to produce an N-type material, or it could be a trivalent atom to come up with a P-type material. Now, if we take a small piece of semiconductor material and dope half of it with a trivalent atom and the other half with a pentavalent atom, that would result in a semiconductor device with P-type and N-type portions, with a PN junction where they meet. In this video, we're going to talk about this PN junction, as it is the basis for diodes. After doping an intrinsic semiconductor material, usually silicon, so that part of it is P-type and the other part is N-type, a PN junction is formed at the boundary between the P and N regions. In the P region, the majority carriers are holes, while in the N region, the majority carriers are free electrons. When the PN junction is formed, the free electrons in the N region begin to diffuse across the junction and combine with the holes in the P region near the junction. This makes the N region lose free electrons and creates a layer of positive charges near the junction. As the free electrons combine with the holes in the P region also loses holes and creates a layer of negative charges near the junction. These two layers of positive and negative charges create a region where charge carriers are depleted. This region is called, fittingly, the depletion region. In reality, the depletion region is formed in an incredibly short amount of time, and its width is very thin compared to the P and N regions. The depletion region will continue to expand until the total negative charge in the depletion region repels any further diffusion of electrons into the P region. This time, the depletion region acts as a barrier to the movement of electrons across the junction. In the depletion region, there are many positive and negative charges on opposite sides, and as described by Coulomb's law, if there's a positive charge and a negative charge near each other, there is a force acting on these charges. The forces between the positive and negative charges in the depletion region create an electric field which blocks the free electrons from the N region to flow across the junction. In order for the electrons to move through this electric field, a certain amount of voltage equal to the barrier potential of the electric field must be applied across the PN junction with the proper polarity. Now, let's try to analyze the formation of the PN junction and the depletion region through an energy diagram. The energy levels of the valence and conduction bands in an N-type material are lower than the valence and conduction bands in a P-type material. This is because trivalent impurities exert lower forces on the outer shell electrons, and lower forces mean that the electron orbits are slightly larger and have greater energy. If we try to examine the energy diagram for a PN junction at the instant of formation, we can see that the valence and conduction bands in the N region are at a noticeably lower energy level compared to the P region valence and conduction bands. But we can also see that the upper part of the conduction band in the N region and the lower part of the conduction band in the P region overlap. In this case, the free electrons in the upper part of the conduction in the region can easily diffuse across the PN junction and temporarily become free electrons in the lower part of the P region conduction band. Temporary because, after crossing the PN junction, these free electrons rapidly lose energy and fall into the holes in the valence band of the P region. As the free electrons from the upper part of the N region conduction band cross the junction, the depletion region starts to form and expand. But the energy level of the N region conduction band also starts to decrease. This process will continue until there will be no electrons left in the N region conduction band with enough energy to cross the junction. At that time, the junction is at equilibrium and the depletion region is complete because the diffusion is done. As you can see in the energy diagram, the top of the N region conduction band and the bottom of the P region conduction band is now aligned, and this time there's now an energy hill that the electron from the N region must climb in order to get to the P region. Another thing to observe here is that the energy level of the valence band in the N region also decreased. So the energy gap between the valence band and the conduction band in the N region remains the same. In this video, we discussed about the PN junction, its formation, and the formation of the depletion region. We also discussed the barrier potential and the energy diagrams of the PN junction and the depletion region. If you have any questions, leave it in the comments below. And if you found this interesting or helpful, give it a like and subscribe to our channel.
Alright, so as we've seen the forward bias condition, yeah, so we've covered the no bias condition. Next, we move on to the forward bias condition. Here is the case where we apply positive supply, and that the result is that there is a significant current flow across the diode, which is well, uh, depends, no? It is the current flow depends on the amount of voltage supplied across the terminals. Of course, the recommended setting is that we install some resistance value in series with the diode. So that's the recommended practice. So as we can limit the currents, no? Because practically speaking, there is somewhat of a maximum amount of current that actual physical diode devices can withstand. No? So you can check that one on the diode specifications sheet. And that, excuse me. Now, if we are to apply the positive EMF, no, through the N type, through the or through the P type material or through the anode, relative to the cathode or the N type material, it will result to the uh, reduction of the depletion region. Right. So what happens is the positive supply sort of cancels out or pulls away the uh, the electrons here, or the majority carriers that migrated from the N-type material. And on the other side, no, on the negative side, it will somewhat do some, not really cancel, but it will pull away the majority holes in this region, which sort of migrated from the P-type material. So this will essentially reduce the depletion region, allowing for further current to move or migrate through this region. Well, what happens is that there will be further current flow across the junction. So that's what happens now if we try to apply potential across the junction. But one thing is that uh, we need to come up with a sufficient voltage level so that further current can flow across the material. No? So the voltage levels are already mentioned last time. For the germanium, we have the zero point 0.3 volts. For silicon, we have zero point 0.7. Typically for uh, the compound semiconductors like gallium arsenide, we have 1.2. But for most rectifier diode applications, we have the germanium and silicon. Most compound semiconductors are used in LED, no, the light emitting diodes, but we will cover more of that in some later discussions. Right, so I guess you're gonna have to somewhat recall these two things, or at least these three things. Now, zero point 0.3 for the germanium, zero point 0.7 or thereabouts for the silicon, and some value greater than 1 volt for the compound semiconductors. So actually, if we try to plot the response characteristics of diodes, is that if we try to apply voltage across the pins, anode and the cathode, well, positively, we need to reach, in this case, some forward potential greater than zero point 0.3 volts. I suppose this one is for the germanium, no? So I guess we have a germanium here. So after we reach zero point 0.3, then it will start to uh, conduct current, no? So we can have a current at least, and that is called the forward bias region. So the region highlighted by the green shade right here, and then right. So for now, we're gonna focus on the forward bias region, no? And then based on the following explanation, and we can see that we can allow for some milliamps current to pass through or to go through the material with the voltage applied, no? As long as we exceed the minimum forward voltage, or what we can henceforth refer to as the knee voltage, no? So I guess you just gonna have to remember those two most common figures: zero point 0.3 for the germanium and zero point 0.7 for the silicon. And here's some further explanation on the forward bias conditions.
In our discussion with the p-n junction, we mentioned that the p-n junction is the basis for diodes. Diodes are one of the most widely used devices in electronics, and they have the ability to conduct current in one direction when forward biased, and block it in the other direction when reverse biased. In this video, we are going to discuss about the basic structure of a diode and learn how to operate it in the forward biased condition. A semiconductor diode is a two-terminal device in which half of it is doped as a p region and the other half is doped as an n region. Between the p and n regions are the p-n junction and the depletion region. The p region is called the anode, while the n region is called the cathode, and each of them is connected to a conductive terminal. Biasing basically means applying a DC voltage across an electronic component, and as mentioned earlier, a diode can be forward biased or reverse biased. In forward bias condition, the current is allowed to pass through the p-n junction, but one requirement to forward bias a diode is that the negative side of the external bias voltage must be connected to the cathode or n region of the diode, and the positive side of the external bias voltage to the anode or the p region. The second requirement is the external bias voltage must be greater than the barrier potential. When these two requirements are met, the diode is forward biased. Now, when a diode is forward biased, the negative side of the external bias voltage pushes the majority carriers in the n region, which are free electrons, toward the p-n junction. It also provides a continuous flow of electrons into the n region through the external connection or the conductor. The movement of the free electrons here is called electron current. With the help of the external bias voltage, the free electrons can now overcome the barrier potential of the depletion region and move on through into the p region. The external bias voltage provides enough energy, but since it takes so much energy to overcome the barrier potential, once the free electrons pass through the junction, they immediately combine with the holes in the valence band and become valence electrons. Then after that, these valence electrons start to move toward the left end of the p region because they are attracted to the positive side of the external bias voltage. The holes in the p region become the pathway for the valence electrons. As the valence electrons move to the left, the holes, which are the majority carriers in the p region, also move to the right toward the junction. This hole movement can be considered as the hole current, or we can also think that the hole current is produced because the holes provide a pathway so that the valence electrons can move through the p region. As the valence electrons leave the p region and flow through the external connection or the conductor, they leave holes behind in the p region. So there's also a continuous availability of these holes moving toward the p-n junction. The valence electrons also immediately turn into free electrons because, as what we've discussed in our previous tutorial, it takes almost no amount of energy for an electron in a conductor to jump from the valence into the conduction band, since the valence band and the conduction band in a conductor overlap. So what happens to the depletion region when we forward biased a diode? As more electrons and holes flow into the depletion region, the number of positive and negative charges is reduced. Since the depletion region was formed because of the two layers of positive and negative charges, the decrease in the number of positive and negative charges causes the depletion region to narrow. When a diode is forward biased, the external bias voltage provides energy to the free electrons so that they can overcome the barrier potential. Now, these electrons give up an amount of energy equal to the barrier potential when they will cross the depletion region. As a result, there will be a voltage drop across the p-n junction, which is usually around 0.7 volts, and an additional voltage drop due to the internal resistance. The internal resistance is called dynamic resistance and is usually ignored since it's very small. You will notice this voltage drop due to the barrier potential when you start working with diodes. From the point of view of an energy diagram, forward biasing a diode increases the electron density in the conduction band of its n region. We will see that the energy levels of the valence and conduction bands in the n region are elevated, allowing free electrons to cross the junction. A key to understanding this is that electrons want to move down and holes want to move up. So, by pushing the n region up more, the electrons can drop into the valence band, or if they have sufficient energy, can move directly into the conduction band of the p-type material. Also note that the depletion region is narrower at the forward-based equilibrium. In this video, we discussed the basic structure of a diode and its operation in the forward-biased condition. We also discussed what happens to the depletion region during forward bias, the effect of the barrier potential, and the energy diagram. If you have any questions, leave it in the comments below, and if you found this interesting or helpful, give it a like and subscribe to our channel.
All right, so we've covered the forward bias region. Next, we move on to the reverse bias. In this case, the anode or the p-type material is applied with negative voltage with respect to the cathode, and in effect, the resistance in this condition is very high. You know? It's typically in the range of mega ohms. Now, the reason for this is that the number of uncovered positive ions in the depletion region of the n-type material increases, no, due to the number of free electrons drawn to the positive potential of the applied voltage, and that the number of uncovered negative ions will increase in the p-type material. So the net effect is that the depletion region widens even further, resulting to a halting, or uh, it will not enable any further migration of ions across the region or across the junction. So you have a very small or zero, essentially a zero current through the diode. So here can be demonstrated, no, that by further applying positive supply into the n-type, you just sort of increasing the positive ions, thereby widening the depletion region even further, right? So the result is the majority carrier flow is reduced to zero, because you've somewhat uh, well, the term saturation does not apply here, because there is a specific uh, condition in semiconductors that we can use the term saturation. But we can see that the entire region is filled with charges already, that it's totally somewhat blocking. However, a number of minority carriers somewhat will not be changing, no, as a result of the or resulting in these minority carrier flow vectors with the same magnitude, with the no applied voltage, no? So the condition exists that the some reverse current somewhat is leaking, no, across the junction. Although it's that's how the physics, no, of these semiconductor materials work. Although it's essentially blocked, but some a very small amount naman for of reverse saturation current exists. No? So and that is that the term we're using is called the leakage current. So it's running across. But that's really a very small value. It's typically in a few microamperes or even less, except for high power applications. But those are different devices, no? Like thyristors that operate on the principle of uh, PN junctions. No? And anyway, we'll not be covering more of those materials in this context. We just restrict ourselves to the typical rectifier diode materials, right? So here the term, all right, so let me just go back to the, here the term saturation uh, comes from the fact that it reaches the maximum value quickly, and no further increase happens in the reverse bias potential. Right, so later we'll see the graphs for that to give us further intuition. And actually, here it is. No? So earlier we've seen the forward active or forward bias region in the upper right side of our plot. Now, shaded here in yellow is the reverse bias region. So you can see in the forward, or if we try to contrast or compare the responses, if we try to apply positive 0.3. No, I think again this is in the case of germanium diode. We have a current of around some currents, no, in terms of milliamps. But if we try to apply uh, positive negative potential, uh, we have a very minuscule amount of reverse current going through the from N to P, no, from N to P. That's a negative current movement, but that is in a very small ranges. No? So it's, you can see in the plot here. This is an actual uh, response curve, no, for an actual commercial diode. And the reverse current is typically in the very fewer than a milliamps or microamps. Actually, in this case, we have around 50. This is in a picoamps, no? Right. So the values of the voltage can be in the order of 10 to 20 or higher, and in the reverse voltage, no. But of course, actual physical devices actual physical devices, there will be some limits to this. No? If we move or higher to this, it tends to destroy the material itself, or burn the material. Right. So describe the events even further. Then kindly check the following clips.
The last time we discussed diodes, we learned about its basic structure and how forward biasing allows current through the PN junction. This time, we're going to discuss about how to operate diodes in reverse bias and see why it blocks the current. If you remember, the negative side of the external bias voltage must be connected to the N region and the positive side to the P region in order for a diode to be forward biased. Now, for a diode to be reverse biased, the external bias voltage must be connected opposite of how it was connected to a diode in forward bias condition. So the positive side is connected to the N region, while the negative side is connected to the P region. In this case, the free electrons, which are the majority carriers in the N region, are pulled by the positive side of the external bias voltage, creating more positive charges near the PN junction. The same thing happens in the P region. The holes, which are the majority carriers, are pulled by the negative side of the external bias voltage, and more negative charges are being created near the PN junction. This results in a widening of the depletion region and increase in the strength of the electric field between the positive and negative charges. If we try to look at the energy diagram in a reverse bias condition, we'll see that the depletion region has now become wider and the energy hill is steeper, which makes it impossible for the free electrons to cross the PN junction. Again, looking at energy band diagrams, electrons want to go down while holes want to float up. In this case, minority carriers in the P and N regions. They are thermally generated electron-hole pairs. The negative side of the external bias voltage pushes the minority carriers in the P region, which are free electrons, toward the PN junction. Since the conduction band in the P region is at a higher energy level than the conduction band in the N region, the minority electrons can just easily pass through the depletion region, since there's no additional energy required. The reverse current in reverse bias condition should be really small. However, if the external bias voltage is increased to a value equal to the breakdown voltage, the reverse current will suddenly increase. What happens is that the high reverse bias voltage gives enough energy to the free minority electrons so that as they move through the P region, they collide with atoms and knock valence electrons out of orbit and into the conduction band. Now, these electrons that were knocked out from their orbit become conduction electrons. They are also high in energy, and so they repeat the process of colliding with atoms that results into multiplication of conduction electrons. Because these electrons possess high energy, after they cross the depletion region, they don't combine with the minority holes, but go through the N region as conduction electrons. The multiplication of conduction electrons causes the reverse current to increase drastically. If the reverse current is not limited, this might cause damage to the diode. So now we know how a diode operates in a reverse bias condition. We also learned about reverse current and how increasing the reverse bias voltage to the breakdown voltage drastically increases the reverse current, which can damage the diode. If you have any questions, leave it in the comments below, and if you found this interesting or helpful, give it a like and subscribe to our channel.
Okay, so we've seen the reverse bias region, but as I've mentioned, no, these can go on until we've reached some physical limits, and this physical limit that I was referring to is called the avalanche breakdown region. Are you guys familiar with the term avalanche? Alright, so that's in the case of since we live in the tropics, no, much of us haven't seen what an actual uh, avalanche kind of looks like, but in many cold regions or snowy regions, no, like in the Alps or mountainous. Well, that should be that sort of combination of mountainous and snowy regions that such avalanche or avalanches can occur, and that is because of the relative instability of the cycles brought about by the cycles of formation and formation of snow on the region, and then the subsequent melting or process, and such cycles just repeats itself, and that is the massive flow downward. So similarly, in the case of semiconductors, or particularly semiconductor diodes, no, an avalanche breakdown can happen if we try or if we exceeded the reverse bias potential. So we've said, or we've seen in an earlier graph, that we can reach until a negative 10, 20, or even 40 for some devices. But of course, there will be an absolute limit. This situation, or this limit is also, or this event and phenomenon is also referred to as the Zener breakdown. No? And the image for the graph is this one. So we've seen reverse saturation condition if we apply negative bias into our rectifier diode. But this is somewhat again exaggerated, because the typical range is in the tune of microamps or even picoamps. But if we move further, or if we increase the applied voltage, we can experience a drastic drop in the resistance, no? In a sense that it will allow for a huge amount of current to go in that direction. And that is called the avalanche effect. And this part of the response curve is otherwise known as Zener region. In a typical setting, or in many commercial diodes, if you reach this, or if you go beyond these voltage levels, chances are is that you can be able to destroy the diode or the device itself. But in some later discussions, we will cover specific types of these devices that is or which are intended to operate by design, no? Using this particular uh, portion of the response curve. All right, some properties that you need to remember is that these parameters, no, the all right, so the current flowing through the diode is related to the reverse saturation current. We have to remember, in this case, the Euler's constant, um and the ideality factor, now whether we're using silicon, germanium, or other compound semiconductors. And as we've always cited or mentioned in our earlier discussions, so much of the temperature measurements that we are observing when analyzing semiconductor properties is in terms of the absolute temperatures. No? So you've seen, so we've mentioned only in the case of 0K happens that zero current occurs. No? So we were using essentially absolute temperatures in calculating the general diode characteristics. This equation is otherwise termed as Shockley's diode equation. It was Shockley who defined or observed much of the physical uh, properties, no, of semiconductors when subjected to some tensions or electrical uh, voltages or currents. Yeah, so this is Shockley's equation applied in diode devices. Okay, so the previous, okay, so the equation applies for the case of the forward bias region and the reverse bias region, but not in the Zener region. So this is a different case now. So you can imagine you have an exponential curve leaning upward, and then that sort of exponential curve in presented by Shockley does not work for the Zener region. So you have to have a separate uh, equation or model to describe uh, the properties of devices in that region. In that we need to take account the resistance of diodes as well, no? Because intrinsically they have resistive properties, and that these ohmic characteristics are needed to be accounted in our design, no? Or if we are to uh, figure sufficient voltage or current ratings for our design, then we have to consider take into the resistance values of these devices. All right. So as by virtue of Ohm's law, we can obtain the resistance values of the diodes using the characteristic curves. No? Now these simplification only works for the region of perfectly uh, the of the response characteristics with the perfect linearity. No? So that is to say that we apply these equations in approximating responses beyond that of the knee voltage. No? If we are to recall, the knee voltage is somewhat higher than zero. Again, we have a zero point 0.3 or zero point 0.7. Then there is some sort of a upward trend. After that, then we can experience somewhat response or ohmic response in this region beyond with a decent amount of linearity. Now, in that case, you can apply the following equation. Basically, this is simple Ohm's law to describe the resistance values of our diodes if we are to operate using or above that defined region. So similarly, if you are to apply AC inputs or AC supply, then the same characteristics can be obtained in such figures, no? And then In this case, an AC input, no, or a sinusoid input applied in the diode is in a somewhat positively offset form. If you can think of if we can think of fluctuating DC, no, so that's a DC with the sinusoids applied. So we can come up with such ohmic values, no, if we are to use uh, fluctuating DC as our input. Right? So I think you can imagine having a sinusoid wave superimposed on. Okay, if you have a sinusoid wave superimposed on a DC, then you can have that fluctuating DC. Right, so I'm trying to search for applicable applicable graphs to demonstrate this. Anyway, so maybe I'll try to use this one. So let's say if you have this graph, no, and you have a zero reference in this side, then you can be able to apply AC. Well, this is actually a DC because all of the figures, even the lowest points, are of positive. But these sorts of fluctuates resembling a good. Well, this is not a good example of sinusoids, but if you think of it as a good plot of sinusoids, then you can superimpose a sinusoid input voltage on top of the DC component, no? So that you have a fluctuating DC input. So allow me to go back to my slides. Yeah, so if you try, right, so if you try to apply fluctuating DC input here, no, DC input voltage, then you can exploit the ohmic region of the diode, and that you can have a current uh, in AC form as well, no, resembling the input response. So varying the input will move the instantaneous operating point up and down, and the region of characteristics, and thus define a specific change in current and voltage as described here. With no applied signal or applied varying signal, the if you don't have the AC component, you have a pure DC in your input. Then you have that middle point as something that you call the quiescence point or the Q point. The designation of the Q point is based on the fact that the output is unvarying in this region. So you can think of any applications now where you can apply fluctuating voltage input here, so that you can have fluctuating current outputs also in the you can exploit this part of the response curves of our diodes. And in doing so, we can sort of approximate some resistance values through the Q point, no? Because you can see we have a slope, or the changes in current as a response of changes in the applied voltage varies somewhat in a positive trend. So you have a positive resistance value here. And in a good amount or decent amount of the response characteristics, we have somewhat, again, a decent amount of linearity. So much of these figures in this equation are derived from experimental figures. But again, as we are using Boylstad's reference, handbook as reference, then I suppose uh, in US, is it in Florida, I think, uh, anyway, in the case of the experimental values presented in Boylstad, they made use of the reference temperature as 27K, and this directly translates to 3 or sorry 27 degrees Celsius, and this directly translates to 300 K, no, in absolute terms. And in such conditions, they you can just plug in the value of fixed constant 26 millivolts, and you have the measured diode current here, and come up with the diode resistance figure right there. So that's called the resistance of the diode in the ohmic region. So similarly, in the analysis of AC responses, we can have the following figures. So we have the average resistance in terms of the AC responses, the change in voltage, no, voltage applied to changes in the current going through the diode. And we can somewhat, what happens is that we just merely linearize this sort of region. We approximate this region as something that can be, well, approximately linear. It has decent amount of linearity, and any error contained in this region will be introduced as some sort of an error with that sort of approximation. Okay, so next we are to be familiarized with the concept of ideal diodes. All right, so in the case of ideal model, we just consider the two states of diode as the on and off conditions. So an ideal diode is just approximated by an open and closed switch. That's it, and that's plain and simple. And that the resistance value for the ideal diode in a forward condition is zero, in reverse it is infinite. If we try to compare the ideal model to that of a practical, a real world diode, we have the difference of a zero point 0.7 volts in the case of silicon rather than zero, and the ohmic characteristics, no, an ideal is of zero resistance, so it's rather a steep a vertical response as compared to the practical diode with some ohmic regions here. So you have a slope uh, that is described by the equations that we've seen earlier. And that for us to be able to come up with a model of an actual or practical diode in comparison with the ideal ones, um, we have the ideal diode model in series with the resistor. Of course, the resistor resembles the ohmic regions we've seen in the plot, as well as some battery model, no, to resemble the zero point 0.7 volts forward voltage uh, bias, no, or a forward potential, no, to turn on the uh, the diode into conduction or forward bias region. For higher voltage applications, if the zero point 0.7 volts becomes insignificant, or in many cases where the resistance values become insignificant, now for high voltage applications, then we can just remove or neglect, no, the value of the resistance, and we say that this value is essentially small. Then we have the following equivalent model. Just have the zero point 0.7 volts to turn on the diode into conduction, and then the ideal model which acts as switch depending on the bias, if it's forward or reverse. So here are some comparison of how various actual semiconductor devices differ. Of course, we have the germanium at zero point 0.3 and silicon at zero point 0.7. Again, we have for compound semiconductors forward voltage greater than 1. And here are some of the specifications to look into if we try to procure uh, or think of models to procure, no, when coming up with electronic designs. Of course, the forward voltage and the maximum currents, reverse saturation current is something we've mentioned earlier. Breakdown voltage, or if you can recall, Zener region. So that's the voltage level when where we reach that Zener region. In many datasheet is referred to as the peak inverse voltage, or peak uh, voltage in reverse. No, so PV, or peak inverse voltage, I think, is the more commonly used terminology for this in specification sheets. And that the power, and then power dissipation is described in the specifications sheet as well. In some cases, if you're working with higher frequency applications or filters, you need to consider the equivalent capacitance values, no? Because we're dealing with semiconductors, and in some cases, some insulated insulation properties sort of resembles these devices in high frequency applications. So you need to look for these figures as well. Reverse recovery time is essential if you're designing for fast switching applications. You need to check how long the switching effect happening. No? So that's expressed in terms of the reverse recovery time. So that's the time it takes for the ions or the charges to move, or to migrate or hold back, now, if you're switching between forward and reverse bias. Of course, the operating temperature range is essential. There are typically there are two range of operating temperatures available. First is the industrial or commercial applications. the higher or heavy duty requirements. Uh, for heavy duty requirements, there's an even higher classification called the military applications. No? So these devices are intended to go beyond the usual industrial commercial ranges, and I suppose these were developed no, for use in extreme climate conditions, no, such as uh, military operations in desert regions. So you have higher operating ranges for those military applications. And so you notice much of which these parameters are temperature dependent, as we've mentioned uh, so many times already previously, that the electrical responses and behaviors of semiconductor devices are very much affected by the outside environment or temperatures in particular. So here are some of the typical characteristics or specifications. As I mentioned earlier, so even in the commercial or industrial use, some devices can go up to 150 degrees temperatures. And then military, I think, can go even higher to 200 or so, maybe. So you might want to check or do some actual comparison of how these specifications can vary. And as again, as I've mentioned, much of these can be affected by the ambient or environment or outside temperatures. Right? So some of the operating characteristics are also plotted in the datasheet to provide us better understanding of the device characteristics. Typical packages of semiconductor diodes are the following. Of course, for the GP, if you can see the model, diode model with the GP at the end, so that's general purpose packaging. For higher power applications, you can notice that there are some even bigger bulk of metallic conductors available for designers. So again, this is for heat sinking mechanisms, no? So that there is a huge metal provisions. So that is to allow for or facilitate better transfer of heat from the device to the going out. No? So that's heat sinking design principles. So we have the DO. I suppose that's diode outline. There are the other diodes in transistor packages as well. So this is supposedly T or transistor outline, but the device itself is a diode. And if I remember correctly, this sort of designation is published by the JEDC or JDEC. That's good. That's the Joint Electronic Devices Engineering Committee. So these guys are based in Japan, no? But they have the packaging standards and nomenclatures proposed or presented by JDEC has been widely commercially or widely been adopted by electronics industries, no, globally. So some means of testing the functionality or operation of diode includes the testers or multimeters, and to check the ohmic characteristics of these diodes, as well as the curve tracer. Using diode testing, you just apply voltage supply, no, using the voltmeter function or the diode testing function. No? So usually you can check the selector switch, and you can point it to a diode tester application. It has usually in some cases buzzing sound, no, if it's okay or not. And just applying, but this device is doing is applying voltage supply across, and then it is able to measure the voltage drop, no, if it's still functioning. So we can see here these guys at a silicon device. Otherwise, you're gonna come up with a reverse bias region. No? So here we have a higher amount of voltage values. And this is for the functional unit. Well, a defective diode, then all right. So if you have a defective diode, it will not open even if you apply the proper forward bias. Or in another case, if you have a burned device, it will just act as a short circuit. No? A curve tracer can even provide a more intuitive uh, data on the response characteristics of diodes by plotting the entire voltage and current responses. And here are some of the key ideas that we've shared in the previous discussion. So kindly check for some of the pertinent details here. Right, so some of the key concepts you need to remember is that without external applied bias, the diode current is zero in the forward region. The current increases exponentially as the voltage increase. In the reverse diode region, the current is a very small reverse saturation current until the avalanche breakdown or the Zener region is reached. As I've mentioned, in many cases or in some commercially available models, if you go beyond this, you tend to destroy the device itself. But there are specific diodes designed to operate in this region, and we will see those some of those devices later. So again and again, you have to remember the threshold voltages for silicon is zero point 0.7 and zero point 0.3 for germanium. Reverse saturation current uh, increases, no? And this is actually observed to be doubled in magnitude for every decade of or tenfold increase in temperatures. So maximum power dissipation happens or is equal to the product of the diode voltage and current, and that the capacitance of the diode increases with the increase in forward voltage or forward bias voltage, and the lowest capacitances in the case of the reverse bias region. Now we move next into the applications. Okay, so here we will cover the load line analysis and some essential rules no when analyzing or designing diode networks. So some of the example sample configurations that we look into are the connections of diodes in series, parallel, and any combination in between. Then we will understand that the differences in DC and AC level inputs, and in a future section of the slides we will have the clipper and the clamper configurations, as well as the applications now for the Zener diode. So that's what I was trying to refer to earlier. There are specific diodes designed to work on the avalanche breakdown characteristics, or using that characteristics. So this is a different type of diodes, but essentially the concept of Zener region is, or it the diode itself is built to withstand voltage ranges no, beyond the Zener region. Later we'll see other special purpose diodes, including LEDs and the photodiodes. Also, I mentioned the Zener, and much of that will be covered in subsequent sections. So again, we have the diode symbol in actual device. So we have the P-type material connected to the, or we term to as the anode, and the N-type material is referred to as the cathode. So we can analyze electronic circuits using characteristics, or through the use of model for approximating the device responses. In terms of load line analysis, we have covered already previously the conditions of the forward bias. We've explained it previously. Now, here we perform load line analysis no, by trying to plot this load line right here, which is the equivalent of applied voltage, and you're gonna have a slope that is somewhat the difference, or the ratio of the supplied voltage and the resistance, and then you plot a curve or a line right there, and the intersection of which between the load line and the diode characteristic curve is termed as the quiescent, or the Q point we've mentioned in the previous sections. To perform this, we have to apply KVL, no? The Kirchhoff's voltage law. In this circuit, as an example, we have the voltage supply minus the voltage drop of the diode, and then the load voltage will be equivalent to VR here. So rearranging the equations, we have the following. Now, once we have, right, so if we have come up with the current at zero, based on this equation, no? Based on this equation, we have the current at zero. Therefore, the voltage across the diode is equal to the supply values itself. No? So straight line is drawn between 2 points defined when you have an off 0 volt across the diode and 0 current through it. And then we have the load line of the network, no? By plotting that straight line. Again, in the previous graph, we've mentioned that the intersection of the characteristic curve and the load line is called the Q point, and that the value of the current of the diode current is described using the equation of Shockley. No? So using these expressions here, then we can come up with the unknown parameters. No? All right. So, but the load line analysis is a much rather convenient. No? So we don't need to do this equation. But these models provide this idea of how the physics works now for these diodes. Again, the more convenient approach is to just plot the load line and the characteristics curve to give us the Q point, and the further analysis of the diode responses can be obtained in this combination. So again, for forward bias diode, silicon base rectifiers can be turned on by applying 0.7 volts across. For the germanium variants, that is 0.3, and for compound semiconductor based diodes, then that's typically higher than 1 volt. Right, so here's a sample problem where we can apply the load line analysis. In this example, we have 10 volts, 500 ohms, and then a silicon diode. Then we have 0.7 volts, no? Or roughly 0.7 volts for the diode characteristics. Right, so first we look into the diode current. No? In this case, the current is all right. So the current is Mhm. Okay. So if we consider the voltage drop across the diode at 0 volt, no, just simply using Ohm's law, then we have the diode current at around 20 milliamps, no, at 10 volts and 500 ohms, right? Assuming you have a zero voltage drop across the diode. Now, in the case of all right, so in the case of a diode off condition, if you have 0 amp current in your ID, and then the voltage drop VD is at 10 volts. No? So that's in the case of the zero current. Now again, if we follow the previous rules here, no. All right. So if we apply 10 volts in your E, and then the E over R here, so you can plot the diode uh, load line using 10 volts somewhere, if you extend it somewhere to the right, and then 20 milliamps, no? And then Q point must rest somewhere in between here. And that Q point is actually, if you try to calculate, is around zero point 0.7 volts, no? Or slightly lower than zero point 0.8 volts. So you have plotted the zero point 0.8 there. And then for the diode, the current, just simply applying or figuring out also the point at which this intersection happens is that it is at around 18 milliamps, no? So around at this point. So if we try to expand this, we can have a better glimpse of the graph. And that the current is at 0.78. So that's your Q point, right? That's your that's your Q point. And if you want to solve for the voltage across the load, here I think the load is the resistor R. So the voltage across that is V sub R. We just again perform KVL, and that VR here is equal to E, which is 10 volts minus the diode potential at zero point 0.7. We've used zero point 0.7. So the load voltage at VR is around 9.3 or lower, right? Okay, so we move on to the next examples. Right, so yeah, so similarly, now we have come up with the resistance values. Right, so similarly, we've come up with the resistance values at 40 ohms. And that is if we apply or obtain the slope of this load line here. Okay, so later we will look into configurations in how we determine the conditions, on and off conditions of diodes. All right. So in some later sections, we will see how the effects of resistance networks and various network configurations of diodes can determine whether a diode is in on or off conditions, right? And we have to remember that besides the fact that the diodes can work as a switch in again in terms of on and off conditions, there are voltage drops that we need to observe in the analysis of these devices. So we can see a diode is in on condition if we apply a zero point 0.7 potential across the element, and that uh, an open circuit can have any voltage across its terminals, but the current is always zero, and the short circuit has a drop of 0 volts across its terminals, but the current is limited only by the surrounding network. All right, so one thing we also have to remember is that when analyzing diode networks, that to check, if the specifications are available. First, if the diode device is defined, if it's silicon, germanium, or otherwise, then chances are is that the voltage drop or the forward voltage is can be identified now using such specifications. For series configuration, the diode is connected in series with other components. Now, take note that for computation of the diode configurations, we assume that forward resistance of diode is usually small compared to the other series elements of the networks. And in such cases, then the internal resistance or internal diode resistance can be neglected. So here is a sample approximation of how ideal diode models are can be represented by the following. Now, for ideal silicon, you don't have the ohmic region considered in your equations. Then you have just a simple voltage source at zero point 0.7, right? In the That's in the on condition. In the off condition, this is just merely an off switch. For again, that's for silicon, for both cases. For the ideal diode, you just have a close switch with a volts across, and then the current will definitely still be zero in the case of reverse uh, region, or in the case of zero current. So that's the symbol is merely equivalent to an open switch. Okay, so considering the following circuit example, no? If you have a diode series configuration, then we can perform this analysis that the voltage drop across the resistor resembled by VR right here is equal to the supply minus the diode, the forward voltage of the diode, or the knee voltage, so to speak. And if this is identified as silicon, then you have a zero point 0.7 volts right there. And then you can obtain directly, the value of the VR, right? And then next, after the value of VR is obtained, you can later solve for the value of the diode resistance, which essentially is the same as supposedly the diode current rather, which is supposedly the same as the current across the resistor, and that is your VR divided by your R. No? You've obtained the VR already, then you can back calculate, no, using the value of R. And that, if we go back, determines whether if we have an open or short or any whatsoever conditions, in this case. So for the other series configurations, in this case we have a reverse bias condition. In such cases or in such event, um, if we substitute this as off condition, we have zero current, and voltage drop is essentially VR. Uh, VD is equivalent to the entire E value. But of course, since you have zero current here, then your VR will also be zero right there. Okay, so now for a further example, you can start. I'll give you these guys now as exercise. So that's just essentially a similar to the previous example. So this is also this is shared in Boylstad's handbook. So here, if we apply a KVL, no, 8 volts minus the silicon voltage drop at zero point 0.7 will come up with the voltage across the resistance at 7.3 volts. No? 7.3 volts is your VR. And then the current across that is uh, ID right there is actually 7.3 volts. No? Because you have again 8 volts minus zero point 0.7, you have 7.3 volts divided by 2.2k becomes around 3 milliamps. So that's the value of your ID right there. So you have to treat the diodes first before going into the ohmic calculations. Now, similarly, in the reverse bias condition, you have zero current through it, and so essentially you have a zero VR right there. So the VD is actually 8 volts, but again, you have zero current. So that will not be, yeah, so this will not be a functional circuit. Right. So and the high voltage across the diode is in an off state. No? So in the previous example, although it has high voltage across, it's in off state because it has a zero current. And an open circuit can have any voltage across its terminals, but the current is always zero. Therefore, the short circuit has zero drop across the terminals, but the current is limited only by the uh, surrounding networks. Right. Similarly, in the series diode configuration, the level of voltage applied across the diode in this example is not sufficient to drive it into on condition. So essentially, this is still an off circuit, no? Yeah. So you don't have any sort of current there because, as you know, it is identified as silicon material. It requires zero point 0.7 volts, so it's not sufficient to turn the diode into on condition. How about this configuration right here? You have a silicon at zero point 0.7. Red LED is defined as having a 1.8 forward voltage. Just add these two guys together, no? So that becomes 12 volts minus, what would that be? Minus zero point 0.7 minus 1.8. I think it's around 2.5, no? So 12 volts minus 2.5 is equal to 9.5. Therefore, your diode current is equal to the resistance, no? The voltage divided by the resistance. So you have the voltage at 9.5 volts. Again, that is in the case of 12 volts minus zero point 0.7 for the silicon, another minus 1.8 for the LED, red LED as provided. Then you'll be able to come up with the VO at 9.5. No? Using Ohm's law again, 9.5 volts divided by 180, then you'll be able to come up with a diode current at 13, uh, greater than 13 milliamps. Okay, so here's another configuration. So in that case, you have a forward biased silicon. However, the other guy right there is a reverse bias. So what happens there is that so what happens there is that although this one should be forward bias and should be able to conduct uh, the same the potential cannot be reached, you know, because this guy right here is deemed disconnected because first it is in a reverse bias condition and there's no light voltage to exceed it to break over um, a region if you think of sort of exploiting that. But essentially, you have a reverse bias here, so the ID will be zero in this condition, and all the other parameters are essentially, well, I think, yeah, yeah. So all the other parameters are essentially zero. Now there's another configuration that we have input resistance R1 at 47K and load resistance R2 shunt to the output at 2.2K. The thing is, in this case, you have a negative supply here. So what happens here is that you treat you include the second supply voltage, the negative 5. You add these two guys together, so essentially you have a supply of 15 volts, because in that loop you have a positive supply minus a negative, no? So that sorts of cancels up, and the effect is that these two guys are actually sort of compounding or adding, stacking up together. So you have essentially a supply of loop supply of 15 volts. Then you have to subtract your zero point 0.7 volts in your silicon right there. And the remainder will be the potential across R1 and R2, right? So again, if we try to calculate those figures, then your overall supply voltage is at 14.3 volts, and the overall resistance is at 6.9 kilo ohms, right? And that the current presented by I there is at around 2 milliamps. And that the voltages for resistors 1 and 2 are essentially uh, obtained using Ohm's law. So you have around 2 milliamps times 4.7K, then you have around 9 point something volts right there. So that's your uh, V1, no? 4.7K. While for the 2.2K, you have another similar calculation, 2 milliamps times 2.2. She'll arrive at around 4.5 volts. So another calculation of using KVL across this or through this loop, then you have a negative 5 volts plus your V2 value minus the VO, no, is equal to 0, or is equal, all is equal to 0. Therefore, your VO is equal to 4.55 volts minus 5 volts. Essentially, you have an output of negative 45 volts. No? So that's I think that's pretty much it. No? All right. So for the series diode configurations, then you have zero point 0.7 for the silicon and zero point 0.3 for the germanium. Let's see if I have the calculations for this one. I don't think so, no? But okay, so the resulting voltage supply is 12 volts minus zero point 0.7 minus zero point 0.3. So that will result to 11 volts. And then applying Ohm's law or first voltage divider for 2K and 10K, then that will be 11 volts times 10. So you have 11 volts times 10 divided by the combination, no? Which is at around 12K. and you have around 9 milliamps na for the current on this one. Similarly, oh sorry, 9 volts no for the voltage across this one. Current is not required, but if you are to apply or divide it by 10k, then you have zero point 0.9 milliamps or 900 microns. And then for the next configuration, we have another supply of positive volt and the negative volts here. So again, you just add these two guys together. No? So you have 10 volts or total of 20 volts. Then you subtract the silicon potential at zero point 0.7 and you'll have around 19.3 volts. So 19.3 volts, then you have the current at 19.3 volts. Then you have the Ohm's law. Ah, yes, is there a question?
Sir, question lang po. Ganito din po ba yung magiging itsura ng exams po namin?
There will be some calculations involved. No?
Tapos may ano po kayo, sir? May copy po ba kayo ng mga calculations? Kasi hindi po ako masyado makasunod eh.
Ah, yes, these are actually directly obtained from the handbook naman. No? So if you check
Thank you po.
ball stat, then you can see these circuits are actually uh, have the calculations in ball stat. Anyway, I'm gonna share these presentations some later. Let me just check na, but I'll share some of these, including the ones with the clips. But the essential thing is that you again the idea of incorporating the voltage drops and the principles of switching in these circuits takes some time to get used to, no? Because it's a little different from what we've done in doing calculations in some resistive networks. No? So it's some a different idea to come up with the practical models, no, with the voltage drops and all those additional concepts. But still, my suggestion is that you guys do a little or more of practice, because again, in this case, these are just application of KVL and KCL, or KVL mostly, and Ohm's law. No? You're just gonna have to add the idea of introducing additional sources or switches in between them. All right. So again, in this example, if you are to solve for VO, essentially, since you have 10 volts here, which is supposedly sufficient to drive already the diode, silicon diodes to on conditions, not to forward bias, then you have a VO at 0 0.7, because this VO is parallel with the zero point 0.7 drops of silicon diodes right there. Now, the voltage across R will be through Ohm's law. You already have the 0.7 here. You still have 9.3 volts for your resistor, and through the use of Ohm's law as well, through Ohm's law, then you have 9.3 volts divided by 0.33 kilo ohms. That will result to 28, around 28 milliamps, no, for the total current in this direction. Now, as you can see, you have identical silicon diodes right there. So you just split the current into two. If you split the current into two, then you have DI and D2 at around 14 yata, no? So yeah, around 14 milliamps. Now for further configurations, this circuit can be rearranged in such a way that the voltage drop across R1 or VR1 is equal to the uh, voltage drop across silicon diode D2, which we've said is around zero point 0.7 volts. We see that the supply 20 volts is a sufficiently large amount. No? So supposedly we can drive both of these diodes, the D1 and D2. Right, so essentially you can have the value of R1 at or the value of I1, which is the current at R1 at zero point 0.7 divided by 3.3 K, and that will be around zero point 0.2 milliamps. No? So that's around zero point 0.2 milliamps. Similarly, we can solve for the value of voltage drop across R2, your 5.6K, by having the supply 20 volts minus the two silicon diodes, zero point 0.7 and zero point 0.7. So the VR2 will be equivalent to 18.6, no? So that's 20 minus zero point 0.7 minus another zero point 0.7. So that's around 18 volts. Applying Ohm's law at R2, you already have 18 volts at 5.6K. Then the current at I2 is at what, 3.3 milliamps. No? So once you've obtained the I2 at 3.3 milliamps and I1 at zero point 0.2 milliamps, then simple KCL will yield or give us the value of current ID2. So that's the current through the second diode. ID2 is just I2 minus I1, no? Since KCL describes the current entering the node, ID2 and I1 should be equal to the one leaving the node. So again, the equation becomes I2 is equal to ID2 plus I1. And I2 minus I1 is equal to 3.3 milliamps minus zero point 0.2 milliamps. So ID2 is at around 3 point something milliamps. Now we have another set of parallel configuration where we have silicon in the forward and germanium in the reverse bias. So essentially here the germanium is switch off while the silicon is switch on, and that what determines ID is the when we perform KVL, no? From the 20 volts supply to the zero point 0.7 drop at silicon diode to the voltage across the 2.2 k ohms. Uh, so these 4 volts tends to neutralize, so this becomes negative. right? So yeah, so this becomes uh, negative supply. So we view this as a negative supply. All right. So for us to obtain VO, then we have to sort of have another KVL in this loop. So this will be around 4 volts, no? Minus the voltage drop across the 2.2K right here. So that's your VO right there. Right. So the determining factor is that this guy, the silicon diode, is the one turned on, and we just disregard the germanium since it's in reverse condition. Another possible configuration is the when you connect two diodes of different voltage drops. All right. So in this case, you have silicon at point 0.7 and gallium arsenide at what was that figure previously? Is it 1.2? No. So what essentially happens here is that once you've turned the silicon diode on, you have a voltage drop of zero point 0.7 across the nodes in between these two nodes, no? So that you cannot go even further than zero point 0.7, and you will not be able to turn the gallium arsenide diode on. And so you can just simplify this by having these components, the supply, the silicon diode, and the load resistor. No? So that will be very much similar to our first example. Just disregard the gallium arsenide device there. So another set of possible combinations is in this case that you have resistors and current sources. Are you guys familiar with this device, current source? Have you seen this before? Can you say show of hands if you've seen calculations of this before? Or I'll ask the other question around. Can you see a show of hands if you haven't encountered this before, the current source device? Again, can I see a show of hands if you haven't or have not encountered this device before, or if you're not familiar with this? Anyone? Okay, so this is a current source that provides a fixed amount of currents regardless of the load. So we model a battery as a constant voltage source, no? But the constant current source is there is no somewhat no exact uh, means or physical implementation other than modeling amplifiers to function as such. No, but in the context of circuit analysis, there are various devices that we can think of or model using a constant current source. So I don't have the calculation for this, but you can think of this as you can perform circuit analysis here using using KCL and Ohm's law as well, no? Or KVL and Ohm's law. So just sort of provide the currents for this as equivalent to the current across the resistor and that of the diode. And you'll be able to come up with the VO as well, no? If you through KVL and KCL, if you're able to come up with the voltage across this one. So yeah, so I think next session we can share with you some calculation for this because I've yet to write this down. And similarly, from the like we've had in the previous examples, we have some combination of supply where we have a fixed positive and a fixed negative. So as you can see, these two things can combine together. No? So you have the effect is that you have around 40 volts together. No? You have a positive and negative supply right there. And if you have a 40 volts supply across the loop, then you just subtract the zero point 0.7 drop from the silicon, and through the Ohm's law, then you can come up with the value of the current based on the value of the resistor in series right there. So that's the current ID. Again, I'll come up with the calculation for this. It's not directly available, I think, in the handbook, but I'll share next time the examples for that. And later we see that rectifier diodes can be utilized now in design of Boolean logic gates to perform Boolean operation. For example, an AND gate has output of high if all the inputs are high, and has an output of low if all the if any of the inputs is low. Conversely, we have the OR gate, which produces a high output if any of the input is high. And we can see some of the implementation in the following circuits. No? So, for example, we have two parallel silicon diodes and uh, load resistor right here in parallel with the output. So, in this case, if we have supplied 10 volts in D1, this will turn the diode on, and then you have VO at 10 volts minus 0.7, so that's roughly 9 volts at your VO. So that's for one input alone. So if we try to apply this guy to the other side, no, and assume for example that we have a VI input, no, at the D1 at 0, and input of 10 volts at D2, then similar output can happen. You also got a 9.3 volts as your V out. So that's your logical, what's that? Logical OR gate, no? Because either D1 or D2 will produce a high output, which is 9.3 volts in this case. Now, on the other side, we have two reverse diode. Well, that is relative to the voltage inputs. And in this case, we have a supply of 10 volts right there in parallel with the VO and the resistor. So essentially, this 10 volts with the input at D2 right here at 0, this will essentially turn the D2 diode on. So you have a zero point 0.7 volts right here. And that can be seen in the voltage output as well. So the VO is equal to zero point 0.7 volts by following or by virtue of the voltage drop across the diode D2 right there. Again, that's in the case of E2 at 0. Now, if we apply 10 volts for both inputs, no, E1 is 10 and E2 is equal to 10 as well, no, assume for that condition, then the voltage difference between E right here and E2, as well as E and E1, will be zero, meaning we do not have current going from the anode to the cathode of both silicon diodes D1 and D2. No, because you don't have a sufficient voltage drop, which is around zero point 0.7 volts, right? And so the output 10 volts becomes directly seen by the VO right there as 10 volts. So that's how AND gate are implemented using semiconductor uh, diode. So you can see here that they need around two devices at least to produce the basic Boolean operations. And another advantage is that these two things, or you can have multiple inputs, no? Or three diodes for to form three or more diodes, no, to form logical or AND gates. Right. So next week we're gonna cover the rectifiers and some subsequent examples forming the basis for design of power supplies. You know, the rectifiers, how AC currents can be converted to DC, which how we create power supplies. You know? So what we can do is I can do is share with you these materials in advance. So you can look into this. Our target is that we can be able to finish until transistors, no, prior to our first quiz. So our first quiz is I'm thinking of organizing something around 2 to 3 weeks from now, at least before midterm. Then this will cover at least diode and transistor characteristics and analysis. All right, so it's pretty much it. Now we will gonna continue the coverage for these materials uh, next week. All right, so our lecture progress will still be synchronized with the other blocks. No? Okay, so are there any questions, concerns, or clarifications so far? Okay, can I see a show of hands if everything is clear up to this point? Okay, so I think so, hold on, let me check my schedule. Yeah, so I think that's it, no? So guys, reminder, no, to that you're expected to form your groups, no, for your uh, term paper and your subsequent year projects, and that each group will be composed of around 6 to 7 members each, at least, no, or at most 7 members. Then, but then if you prefer to work with smaller or on smaller groups, then uh, feel free to approach me if that's the condition. And again, I will check for the final versions of this presentation, and later I'm gonna share this with you, for you to work on some practice exercises. But my best recommendation is for you to check the handbook, no, of Bob Boylstad, no, and try to work on the sample problems so you can improve on your circuit analysis. Of course, you can be able to analyze circuits faster, than it will be uh, convenient for you uh, to have those sorts of skill sets during your exams. No? And I think that's pretty much it for me for this week. If you have questions, concerns, or clarifications, just feel free to send me a message. Gmail function, email, or chat will work. And that's it, no? And have a great week ahead. And I'll see you guys next week. Thank you and stay safe.